What if the key to unlocking the full potential of quantum computing lies in particles we once dismissed as irrelevant? Meet the Neglectons, a groundbreaking rediscovery that could reshape the future of technology. Quantum computing has long promised to revolutionize problem-solving by leveraging principles like superposition, where a quantum bit or qubit can exist as both 0 and 1 simultaneously. Think of Schrödinger's famous cat, both alive and dead in a thought experiment. Qubits operate in a similar paradox. But here's the catch. Qubits are incredibly fragile. Environmental interference can easily disrupt their quantum states, making stable quantum computers a daunting challenge. And this is the part most people miss. What if the solution isn't in creating something entirely new, but in reevaluating what we've already discarded? In a recent study published in Nature Communications, by reintroducing mathematical elements once deemed irrelevant, they've shown how a quasi-particle called an Ising anion could bolster quantum computing's resilience. These revived components, dubbed Neglectons, could be the missing piece to overcoming qubits' fragility. But here's where it gets controversial. Ising anions, while powerful, are not universal. They're like a keyboard missing half its keys. Is this a deal breaker or an opportunity for innovation? Ising anions, confined to two-dimensional systems, are central to topological quantum computing. Unlike traditional particles, they store information not in themselves, but in how they loop or braid around one another. This braiding process is remarkably resistant to environmental noise, making it a promising foundation for stable quantum systems. However, their limited universality has been a stumbling block, until now. The breakthrough lies in revisiting non-semisimple topological quantum field theory, a framework for studying symmetry in mathematical objects. But here's the twist. In this theory, particles with 0 quantum dimension, typically discarded, are reinterpreted as having value. By assigning these neglectons a new form of weight, researchers have unlocked their potential to fill the gaps in Ising anion's capabilities. With just one neglecton added, the system gains universal computational power through braiding alone. Why does this matter? In 2 dimensions, particles like anions exhibit unique behavior. Unlike 3-dimensional particles, whose loops can be undone, anions' paths remain entangled, giving rise to entirely new physics. This entanglement enables superpositions, the cornerstone of quantum computation, while being naturally shielded from noise. But the question remains, can this approach truly bridge the gap between theory and practical quantum computing? While topological quantum computers aren't on the horizon just yet, this discovery suggests a paradigm shift. Instead of chasing exotic materials, researchers may need only to reframe their understanding of familiar systems. Is this the future of quantum computing, or just another step in a long journey? We want to hear your thoughts. Share your take in the comments below.